Hey kids, Smath here. So we're in thermodynamics now, the second thermodynamics. We've already done some thermodynamics. We did delta H equals MC delta T. We did phase change diagrams where we converted ice up into water and steam. We did that in Thermo 1. Now we're in Thermo 2 and we're going to develop spontaneity. So our overview for this is we're going to look at delta S, which is entropy. That's going to be a measure of disorder. And we're going to look at delta G, which is called free energy. And that's going to be a measure of spontaneity. Will a reaction occur? That's a biggie right there. Okay, but before we get to free energy, we got to go through entropy. Entropy is the law of nature, basically. It says that most processes in nature, reactions, they move towards maximum disorder. So life becomes ever increasingly more complex. And that is true. Now, entropy is going to be measured in a unit of joules per Kelvin mole. So what does entropy depend on? The disorder depends on the temperature of it and how much you have of it. That's what we're looking for. An increase in disorder means an increase in randomness. The way we would think about that chemically is splitting things up, turning liquids and solids into gases, that sort of thing. An increase in entropy increases the likelihood that the reaction will occur at a given set of conditions. So changes in entropy, I've already alluded to this. These are changes in state, solids and liquids splitting into gas. That's increasing S. Splitting an object up, dissolving it. All right, and then reactions having more, so increasing. So if we thought about delta S down here, we could explain this in terms of delta S of a solid is less than delta S of a liquid, which is less than delta S of an aqueous system where we dissolved something, which is less than delta S of a gas. And just for some of you, we could say plasma. We don't deal with plasmas very often, but that's where they would be. They're very high energy, heated, charged, gaseous particles. So they're going to be way up there. Now this entropy calc that we're going to do, its symbol is S, and I don't know why it's S. Its unit is joules per Kelvin mole, and the standard is going to have this little degree sign for it. It looks like a 0, but it's really supposed to be a degree sign. And that's going to mean it's happening at standard conditions, 25 degrees Celsius and 101 or 1 atmosphere of pressure. Now notice, these standard conditions are thermodynamic standards, not gas law standards. Gas law standards, remember, were 0 degrees Celsius. These are thermodynamic standards, and they're going to be at room temperature, 25 degrees and 1 atmosphere. To find and calculate entropy then, we're just going to do a matter of products minus reactants right here. That delta S of the reaction is S of products minus S of the reactants. And there's a table I'm going to post that's called thermodynamic data that's going to have all these values for S. Okay? Now, before we get to calculating what delta S is, what the question is going to ask is predict. See these questions right here? What are the entropy changes for the following? Instead of saying what are, we probably should say predict the entropy change. Would we expect entropy to be positive or negative for these two systems? And so in this first system, we're looking at calcium carbonate that's going from a solid to a solid and a gas. So states of matter are increasing. You're going from a solid to a gas. Also look at the number of particles. You're going from 1 particle on the reactant side to 1 and 1 2 particles on the product side. So we would predict a positive delta S. Now, why is it delta? Because this entropy is constantly changing. It's not static. It's always increasing or decreasing. So instead of saying entropy is, we say delta S. That change in entropy is. Let's look at the bottom one. Now we're going from 2 gaseous particles, 2 gas, to 2 gas and 1 to 3 gas. There's no change of state, but there's an increase in particles. Increase in particles means increase in delta S, and these are favorable reactions for a reaction to occur by itself spontaneously. So these are predict delta S. Now that's entropy. We need that as one of our players for spontaneity. Spontaneity is delta G. So spontaneous reactions occur naturally by themselves. They will favor the formation from reactants towards products under certain conditions. Okay? Non-spontaneous are reactions that do not favor the formation of products. They're not favored. They're not going to work. They're going to be lousy reactions. Okay? Now, a couple of notes on spontaneity. I'm moving through these pretty quick. Spontaneity has nothing to do with speed. I've made this point several times in the last few videos that the speed of the reaction is one thing. The equilibrium, how far it lies to one direction or the other, is another thing. And the third thing is, will it happen by itself? So these 3 things fall independent of each other. Not just exothermic, but endothermic ones, okay? So these are going to happen, but they may not be dependent on that rate. These are determined by enthalpy and entropy. We've got to have all 3 things. The big takeaway from this is right here, negative free energy means that the reaction is spontaneous. Okay, so this free energy is what's called the energy available to do work. This was developed by a guy named Willard Hosea Gibbs. He has a nice statue on Yale's campus right outside of the chemistry building. Very, very nice. Okay, and this is energy that we can use our system to do something with. It doesn't imply that it's efficient, but it's energy that's available. Nothing is going to be perfectly efficient. So most chemical reactions, most life runs at about 70% efficiency. Machines run at 30%, we're doing pretty well. All right, so from a reaction, if the change is negative, and so in this case, negative delta G, then it's spontaneous. If it's positive, it's non-spontaneous, and you have to put energy in to do this, okay? This is our free energy. Why is it G? Remember Willard Hosea Gibbs. Gibbs's free energy, and that's why it's delta G. So when do we get negative free energy? Well, when heat is released. Now this slide is really kind of confusing. I'm going to post another thing that's going to give you a nice little chart. But what this says is when heat is released, so negative delta H and entropy increases, positive delta S, then we're going to have a negative delta G. That's the takeaway on this first set. On the second set, when is it going to be a positive delta G, non-spontaneous? Well, the exact opposite. Heat is going to be needed or absorbed. It's endothermic, and the entropy decreases. It becomes more ordered. The other 2 have to do with temperature and how the temperature changes and affects. So these are the theory behind it. There is a chart in your book, and as I said, I will be posting that as well. I thought it was a little bit too much to be putting right in this with all this information. So our free energy calc is Gibbs's free energy, delta G, is equal to delta H minus T delta S. This is our equation, all right? It's spontaneous if G is negative, non-spontaneous. If G is 0, then the system is both spontaneous and non-spontaneous. It's flipping back and forth and doing both things. So this is the setup for what entropy is, what free energy is, and we've covered the two conditions that affect spontaneity: entropy and heat, enthalpy. In the next video, we're going to do some calculations with these numbers. I'm Smath. I hope this video helped.